This is a repository if you want to follow along with the stuff what I'm going to be doing. There is also, on my account, you can find the repository for the Massiv library itself. And also I was talking about scheduler. This is a separate repository for the scheduler. There is a bunch of examples. If you want to play around with them later on or right now, you can do that. Just so you know, I'm going to be sitting and talking, so I won't be able to see if you are asking any questions or anything. So just shoot out, don't be shy, and I will try to answer. Okay. Let me go ahead and turn off the light, because this way it's going to be easier to see. Okay. How many of you were here for the previous 3 sessions I was doing? Almost everyone? Okay. There is something that I left out unintentionally. I'm going to talk about it right now because it's a very important and cool topic in arrays, namely slicing and extracting, how it's done in Massiv. First of all, there is, again, a hierarchy of classes. Every class is pretty much almost self-explanatory. Resize is an array that can be resized. All resizing is usually done in constant time because it's just changing one variable size. Extracting, you can extract a sub-portion of the array. We will see an example of that. And then there is outer slicing, inner slicing, and just slicing. I'll show you some examples what it exactly means, outer and inner. It's not I don't think it's an official terminology, but something I came up with. Maybe somebody else uses it, I don't know. First of all, let's go ahead and look at an example array. This is a sample 3-dimensional array that goes from 0, 0, 0 to 4, 2, 6. And this from IX2, it just converts an index to tuples. And then we compute it as in a box array. It's a synonym to doing something like this, just in case the top part is too concise for you. So the 3 dots is range inclusive, and well, obviously that's an F-map. So let's go ahead and see what the array looks like. Okay, we can fit it on the screen. Good. And we see what we probably expect, just the indices, nothing particularly interesting, but what we can do with it, just to know that this is an unboxed array, so it's represented in memory. We can do constant time indexing, but we also can do constant time slicing. Whenever we slice an array, what means it's not going to create any other arrays, it's just going to manipulate indices to give you an array that is a slice of this one. And how do we do this? If we want to do an outer slice, that's what it means. If we want to take a page at an index 1, we just run this. Very simple. It gives us the page. Every index here is 1 at the outermost dimension. If you want to go do a slice from the inner side, we do something like this, and it will give us a slice where every last index, the dimension 1, it will be all zeros. And if we squint here, every one of them is 0. So it's this thing right here. What about if we want to do a slice from within? We give it a dimension which we want to slice, and then we give the index of a index on which we want to slice, and we get something like this, where every single one of them is 1 in the middle, and that's the slice of the array. And at any point, this is just index manipulation. Does it make sense so far? It's not too complicated, right? It's okay, good. We can go ahead and chain those operations. So if we want to take a page index 1, then row index 2, we can go ahead and do that. There you go. Then what if we want to do a page 1, then row 2, and then 0 element? Yeah, we can do that as well. So it's an alternative way to index into arrays, if you wish. Just slice them out until the last element. Now, you won't be able to, again, you won't be able to slice a delete array all the way until the element, but you can still slice all array representations, almost all of them. Let's look at, yeah, this is the type of this operator. It says, if you can do an outer slice on this representation, and you give me an array and an index of the outer dimension, it will give you back a type family, it's ELT, which stands for element. It's necessary to do that because depending on the representation and index, you will get always, not always, often different result type. It can be an element, it can be an array of the same representation, or it can be a different representation. So that's why there is this ELT. But if you don't think about it too much, usually you'll get an array or an element. It does the straightforward thing for you. What about bounds checking? If we try to slice on dimension that doesn't exist, or the index, we'll get an index bounds exception. And it tries to do something saying like 10 is not safe for the size of 5. For this, this is a pure exception, which makes this function partial, and we don't like those. For that reason, we added safe counterparts for every operator. If we look at those, it's just like this operator, the type signature, except we also get a monad throw, and it always returns a monad throw, which can be a maybe, an either, or an IO if you wish, any other instance of monad throw. Why is it useful? Consider this. We call this function in this operator in IO. We run it, we get the same index out of bound exception, but this now is thrown inside of IO. What if we don't want to be in IO? If we give it a default case, an empty array, and call from maybe, then the M is restricted to maybe, and boom, we get an empty array instead of an exception. Why is it the most important part about pure exception and monad throw is, let's say here, we slice all the way down. By the way, we'll look at the type signatures for those operators, so it can be a little clearer what's going on here. This operator here, it's just like the one with the exclamation point, except it itself takes an action that returns an array. This is done just so you can easily chain them like that. No other reason. Now, whenever I run this, where do you think the exception is going to be thrown? At this line or this line? First or second? Ready? Okay, I'll ruin it for you. It's going to be at the first one. Okay, it's sort of interleaved. Let me fix that. Okay. What? Yeah, somehow Dante interleaves the output, which is weird. The exception is getting thrown as soon as we try to index it. On the other hand, here, this is done, the exception will be thrown purely. So it will be thrown whenever we demand this value, which is going to happen when we try to print it. See, And that's a very important difference, because once you, if you're not familiar with that, you can get exceptions in weird places where you don't normally expect them. So whenever you get a chance, try to stick with monothrow. All right, let's do oh, by the way, this is just something for fun I was doing. If we flip this operator, then we can use the monadic bind, and it kind of looks the same as below, but not really. I don't know. It's not particularly important. Let's do something real. Everybody knows matrix multiplication. If you don't know, it's very simple. First, we need to define a dot product, which takes two vectors and multiplies them pointwise, and then sums the elements. This is how you define it in Massiv, just as you would do with anything else, pretty much. Let's look at type signature. What it requires two source arrays, R1 and R2, and make sure that the elements are numbers. And it doesn't even care that those are vectors, that's a fourth dimension or not. We could restrict it if we want to, but it doesn't care about it. Now, if we want to define matrix multiplication, okay, what do we need? We need two arrays. We need to get their size, M1 and N1, M2 and N2. We need to make sure that inner dimensions agree, otherwise we throw an error. And we create a new array. Here we make sure that their computation strategies combine monoidally. So if one of them is sequential, another one is parallel, it will choose parallel, and so on. There is a monoid instance. It creates an array of M1 by M2. And for every index, we take a slice, outer slice, and we take an inner slice. So we take a row, we take a column, and we do a dot product on them. And let's run this here. There is, by the way, there is already multiplication of arrays implemented with this operator. It's a little bit more optimized than this implementation, but just for the same sake, we run both of them. Yeah, we create two small test arrays, we multiply them, and we get sensible result. Does this implementation make sense? Anybody confused about it? No? Okay, good. Let's look at the type signature. Anybody's confused now? It's not that scary, I promise you. We take one array, we take a second array. Let's look at their representation, and we produce an array of representation R1. What it requires is that R2 is you can take an outer slice of it. The R3 you can take an inner slice of it, which is because of these two operations here. And we need to make sure that whenever we take a slice off, the result is also a source array. If you write in a function like that in your own code, you can just go ahead and restrict it to a particular representation, and then you have a bit of easier type signature. For example, if I want to do unboxed double, unboxed, and this representation is delete, double, it should compile. Yes, it does compile. And this type signature is well, readable, and it will actually be faster as well, because GHC will specialize. It will optimize a little better, usually. This is true not only for Massiv, it's true for all Haskell functions. Less polymorphic it is, usually it's better optimizable. Now, the cool thing about it is, if either one of these arrays contains a parallel computation strategy, this array multiplication will be done in parallel for you automatically, which is very nice. Now let's talk about extracting. We'll have that sample array laying around. Yes, it's here. This is our sample array. And if we want to extract some sub-portion of it, we can use this extract_m function, which also has monad throw. What it does, it takes an index where you want to start your slicing, extracting, and you give it a size of the resulting array. You give it an array that you want to take a portion from, and it will give you again this ELT representation thing of which is going to be an array. For any manifest representation, this will be m. For delay representation, this is going to be delay representation. Now let's go ahead and do a slice. And here we have a 3 by 2 by 5 array, which has started at 1, 0, 1. You can see it here, 1, 0, 1, and it went up to the last element. Okay. If we want to do extracting and then also lower the dimensionality, then we can go ahead and afterwards resize this array. So we first extract and resize, and from a 3-dimensional we went to a 2-dimensional array by 3 by 5. Of course, whenever we resize, we need to make sure that number of elements is exactly the same. So 3 by 1 by 5 should be equal to 3 by 5, which is okay. If we do something like this, it's gonna blow. It should have blown up in my face. I'll take a look at it later. Now, this is what I had to say about slicing. Anybody has questions about it? No. Now I'm gonna talk about integration. Okay. This is an array library, so at some point, one point or another, I had to throw some mathematics at you, so this is what we're gonna do. If you don't remember integrals, it's okay. I will quickly remind you. Let me go ahead and turn on the light. I'll use the board to explain what we're gonna do. Let's say we want to compute an integral of a function from a to b, some f of x, d of x. What if we can't compute this x, the integral of it? We can estimate it. That's what we do in computers. That's why we have powerful computers. How do we estimate the integral? There is 3 different ways that I know of how to estimate it. It's midpoint rule, trapezoidal rule, and Simpson rule. And the latter one gives you better precision than the former one, and they're a little bit more expensive as it goes on. We're going to talk about trapezoidal rule. Let me go ahead. Zoom a little bit. This started as a Stack Overflow question. Somebody asked me this question, not me, asked a question on Stack Overflow, and I found it cool, especially considering that I already implemented in Massiv. So I did go ahead and answer, and we're going to go through those examples. But first, let me explain what a trapezoidal rule means. Let's say this is our function f of x, and we go from a to b, and this is our f of x. What do we want to do? We want to take a bunch of sample points at equal distance. Let's do this at some xn and xn plus 1 plus 1. We compute f of x n and f of x plus 1 n plus 1. And then what do we get here? If we connect these dots, we get a trapezoid. And then we can just compute this area, and then we can do it many, many times across the function, this function, and we estimate the integral. Pretty straightforward. The midpoint is a bit different. Simpson rule is, requires 3 points. Here we require just n portions of it. Okay. Let's go ahead and look at the implementation. How we estimate this. It's pretty visible. I'll keep the light on. Okay. Oh, by the way, I remembered why this is broken. I fixed it already. There was a bug that I found at Zurich Hack, and it's now fixed. I'm using the older version. Okay, good. Now, oh yeah, this is the trapezoid. If you like formulas, this is the actual formula for it. This is what it does. All right. This is the internal implementation that is available in Massiv. We can do this integration along multiple dimensions, and it's also automatically parallelized. It's a lot more general than just a simple function. For example, if you want to do this. Yeah, it'll give you an estimation in this example in 2 dimensions, but we're not going to talk about that. Just wanted to show it for your information. Now, this was a function from the Stack Overflow question. It uses lists, and the question was, how can I parallelize this? If you want to parallelize lists, you're doing something wrong, because it's very, very hard to get a good performance boost with lists. Normally, in this particular implementation, the lists will be completely fused, and it'll be a tight loop, so it works pretty efficiently. But once you're trying to do all sorts of par and par map, I've never seen a good speed up. Oh, this is exactly what it is. Okay, step, it's essentially the delta. Segments. Segments is it's these points from x0 going all the way up to b, and then the area is a list of these areas in trapezoid, a bunch of them. You see, multiplied a step, multiplied by f of x, f plus next step, and divided by 2. This is the formula for area of the trapezoid. And then we just map this function area over all the segments, and we sum them up. And we get an integral. So let's do a sanity check. Integral of function, the identity function. It's pretty much just 10 times 10. It's the area of the triangle. There you go. It's a 50. So we're good. Works on a simple example. Something more complicated like a parabola. It also works. It looks like it gives us some sort of answer. Let's see how good this answer is. If we compute this integral manually, just remember in our calculus course, we get this answer. So it's pretty good estimation. If we increase the number, actually let's do it this way. If we increase n, so do like this, it'll give us slightly better answer each time. The higher the n, the better the answer. Very simple. Okay. So how do we do direct, just the naive translation using Massiv? Let's put him side by side. Okay, this is the original implementation using lists. This is implementation using Massiv. Who can see the difference? Okay, I'll give you a hint. Here's a list construction, here's a Massiv array construction. Everything else is the same. That's certainly neat, right? But it's still, it's a naive translation, and here's the reason why I'm telling you what the biggest problem with this is. For every segment like that, as I drawn, f of x is evaluated twice for every point except for point A and point B. Do you see why that happens? Yeah? Okay. This is because we get segments, and for every, we map for each segment, for each x, we compute f of x, and then we compute f of x plus 1. So there is redundant computation. This is bad. We need to fix that first. Go ahead and do this. First of all, I want to improve this implementation a little bit. First, let me do this. This is essentially a synonym for this. So if we run this, ... it's exactly the same as range inclusive sequentially from 0 to 10. Same thing. If we want to do like other languages do, like let's say Python, they have a range function, the last element is not inclusive. And there is a special operator here which does the same thing, and there is a function range that just go up to n minus 1. It's just for convenience. The implementation is very, very similar, so we don't need to do about it too much. Oh, yeah, we want to check if the implementation gives us the same answer. And yes, it's exactly the same as in list implementation. By the way, the question was, how do we parallelize this? Let's look at those implementations side by side as well. This is the sequential, and this is the parallel implementation. So all we changed was this, and the whole algorithm was parallelized for us, which is sort of nice. Just so you believe me, I'm gonna run some benchmarks. Okay, hopefully it still compiles and runs, and I didn't mess it up anytime in the past couple of days. While it's compiling, oh yeah, we want to check that the answer is still the same. Yes, it is still the same. It's correct. Now here we go. This is the implementation that is built in Massiv. Get 11. The naive list implementation, as you can see, it's slower because it does duplicate work. Array implementation is a little bit slower than list implementation because there is a little bit of overhead over there going on. But that's not terribly important because parallel version is much, much faster. If we use 4 cores, we get a 4 times speed up. Okay, now let's go ahead and fix the problem of duplicate computation. Yeah, here we're going to simplify a little bit. This was the thing that was creating the range, the x values. This is what we're going to do here. There is a built-in function in the Massiv that can do that. It enumerates from a starting point 10 with a step 0.5, and it will produce 5 elements. So let's see what this was doing before, and this function does it for us. Make sense? Yeah? Cool. And let's go ahead and fix this for lists first. By the way, this step thing, delta, it will never change, so you don't need to think about that. Let's look at the y's. Those are already f of x's. It's not x's anymore, it's f of x's. Some list comprehensions from 0 to n, and compute f of each element. This will give us all the points on the top of the function, on the function. And then what we need to zip with this area function. It just computes the area of a trapezoid over y's and tail of y's. And this will get rid of this duplicate computation, and everything else is pretty much the same. The answer is the same too, which is good. Any questions about this sort of optimization? No? Okay, good. Well, let's go ahead and do the same thing in Massiv. We use this function that I just showed you to create the x's, then we map f over it, so this will give us segments there, which is points f of x. And we do the same thing. We do a zip with the function area over the segments, and this is a sort of tail thing. It extracts from 1 up to a size. And then we just compute the sum of these areas. Very good. But the problem is, this segments thing, this array is still, it's a delayed array. So this problem was not solved for us at all, because every time we index into a delayed array, it'll do the duplicate computation. Let's check that it's at least correct. Yes, it is. And in order to fix this, all we gotta do is we gotta convert it to some manifest array. We just compute it, and then it becomes just regular lookups. And then we go ahead and sum it. Everything else still the same. All we needed to do was just compute this segments array. Let's go ahead and no duplicate. See the benchmarks? It's always a good idea to benchmark. Oh. No duplicate. Let's do this. Okay. Okay, list benchmark. List implementation got faster. Array bad got slower, but array sequential now is much faster, so twice faster. But parallel version is even more faster. It used to be, see if I can do this. No, I won't be able. No, never mind. So we did pretty good, but can we do even better? Can we avoid this allocation because we allocate an array in memory? I would think that we can go ahead and get rid of these allocations completely and do it just as a tight loop. Yeah, this is the parallel implementation. All we had to do is just stick a par in here, and that's it. Okay. So this is implementation using lists without any allocation. Well, it wasn't really allocating for it. Ah, by the way, it was whenever we were using zip with here, now GHC cannot create just a loop. It will have to use lists. They will be created, so it cannot get rid of them completely. because we using y is here and y is here, for this reason, there's not going to be just a untitled loop. So here we go. All we got to do is use a fold. Let's look at this. We still, again, create a segments, just as we did before, except we start at 1 instead of 0, and we go up to n instead of n minus 1. This formula is still the same. And instead of sum, we do a left strict fold with the accumulator started at 1. And the first element is f of a. This was the 0 case here. Instead of having it in a list, we start with it. And here we go. We get our y0. We do accumulator plus area of y0 plus y1, and we return the previous element. And there you go. It's pretty straightforward. This way we can go ahead and avoid the zip width, and this should be even faster than the previous implementation. And exactly the same way we do it for Massiv. We create this range, just as before, and we use the function fold ls. And in fact, we could have done the same thing here. It compiles because delayed array is in an instance of a foldable. And it shouldn't affect the performance or anything like that. But just so you know, there is a separate function, fold ls. The reason why we need it because there are other representations that you can fold, but they're not instance of foldable, such as unboxed, because there is a restriction on an element. And of course, we need to make sure that we keep our accumulator strict, because the folds are strict, but up to weak head normal form. This way, otherwise it will give us very inefficient, leaky, memory leaky code. Go ahead and do the benchmark. No duplicate, no allocate. Actually, in order to be able to compare them, I'm going to do it here, no duplicate. Okay. Oh, I'm running the wrong one. Okay. No. This was the same benchmark that is before. Now let's do no allocate. See how that goes. By the way, this is how my life usually is. I'm just sitting and running criterion all the time. And you can see that list got faster, array got faster. Oh, list got even faster than array. And which is pretty good. Now here is also a parallel version of it. I'm going to show it to you. I don't think I'm going to go over it because it's a bit harder to parallelize the code, but I'm going to give you an idea how it's implemented. Now that's all pretty good from original. What was the question? Original LT 18 milliseconds. We went down to I think like 3 milliseconds, and sometimes it's about 3 milliseconds, which is pretty good. Now let's look at this parallelized version that doesn't allocate any memory. Straightforward, isn't it? Okay, I'll just hand wave it. What it does, it's takes an array and chunks it up. It computes the integral in one chunk in parallel with another, and then it combines the results. That's pretty much parallel fold. There is a function fold LP in Massiv that allows it to do such parallel folding. The problem with the initial element over here, it was a little bit tricky to use that. So I just unrolled it myself like that. If you want to dig through it, you can find it in a repository. If you have questions, also please shoot. Okay. Yeah, this is just step by step what it does. We can run it. Yeah, here's the chunks that I was telling you about. It integrates them separately, and then this is the full array. Now, let's see. We have 9 minutes. I think I can also explain a little bit what a Runge rule is. Have anybody heard about Runge rule? It's by the same guy that did the Runge-Kutta differential equations. So, but this is estimate an error. So you can iteratively integrate the function, and it will you can give it what sort of error would you expect, and it will do as many steps as necessary. Let's go ahead and look at the formula. Can you read this? Sorry, this is the only good place I was able to find the explanation was on Russian Wikipedia, so I'm going to go ahead and translate it for you. The I means the integral that we just were computing, integral estimation with n number of points. 2n means the same integral estimation with 2 times n number of points. Okay, so we compute this 2n points, integral estimated with n points. We'll find absolute value and multiply by theta, where theta for the trapezoids is 1/3. For Simpson rule is 1/15. There is a more complicated formula that calculates those. We don't need to worry about that. And therefore, in order to find a good estimation of the integral, we compute it for as many of n is necessary until our delta is less than some epsilon that we specify. And that's exactly what it says over here in Russian. Any questions about this Runge rule? No? No? Okay. Let's see how it's implemented. Obviously, there's going to be some sort of loop. We need not every function we can compute up to the precision, so we need to make sure that we're not going to loop forever. We give it a maximum number of n that we want to stop at. We give it the epsilon precision. We give it a starting value of n. Usually 2 is a good starting point. And we give it a theta, which, as I was showing you, it's 1/3 for trapezoidal. And we give it an integral estimator. This is just a very general Runge rule I just wrote up for the hell of it. And in case when we don't get to the precision we wanted, it will return a left double with the result. In case of stopping early before the n max is reached, which means we reach the precision, it will give us which step number and the actual result of the integral. Okay, so the loop is very straightforward, and max stop. Otherwise, compute that absolute value less than epsilon, good with stop. Otherwise, just go for 2 times n. That's right, wake him up, wake him up. I'm just kidding. I totally understand, yeah. When you implement it, it's not that boring. When you listen about it, like, what? So this is the trapezoidal rule. We call this Runge rule. This is just the power of 2 number, and max. Give it an epsilon, starting at n2, 1/3 theta, and this is the integration function that we implemented just a little bit above. And if we run it, this is what it gives us at iteration at end 1024. It gave us an answer that is up to this precision, which is pretty good, which is exactly what we were looking for. Now again, there is a problem with this implementation. Anybody can see what the problem is? Okay. I'm gonna point it here. Let's say we start with 1, 2, 3. We start with 4 points. We compute the integral estimation. We remember the value. Then we compute for 8 points, right? Including this, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, twice. Anyways. But we again have to recompute f of x for every previous point that we did compute. And that's a problem because we'll be recomputing. At each iteration we have to recompute all the previous ones. We don't need to do that. We can just reuse the previous ones. All we gotta do is compute f of x at the step 2 times delta. And this is exactly the implementation right here. We compute the current segments at the step 2 times step, and the size half of the n. But we also get the previous segments, which are of the same size. And then we create an array using this the loaded array. What this allows us to do is to create an array of size n plus 1. With the default element 0, but that's not important. If you don't remember, I just want to remind you what this function does. It gives us a function that can write into the array, into the resultant array at some point whenever it's going to be computed by this function. And we for loop over the previous segments. We get an index, we get an element, and we write it at every even position. And the current segments we write at every odd position. And this way, we can reuse the previous elements computed and compute the new ones and combine them together interleaving. And this is our segment. And same thing with the trapezoidal rule as we've seen before. That's just the zip width and over the segments. Okay. And here is our memoized, as I call it, trapezoidal rule. It starts with n2. We can just create a quick array with f of a and f of b. This is our start and previous segments. Give it a functions a and b, and it just runs this function iteratively over and over. Now, by the way, here's something cool. An array, you see? Yeah. You guys familiar with overloaded lists extension? Yeah? No? Okay, so we can do this. It's not going to compile. It's going to say I cannot unify double with double of list, no, list of doubles with array of doubles. So all we got to do is turn on the overloaded list extension here. You can see that it was enabled here. Go back to our function, and it should compile, but it, let me see. Oh, it doesn't know what's the resultant array type. Anyway, usually you can do that, just so you know. Okay.